Good morning, everybody, and welcome to Physics 252. We were supposed to meet last Thursday, but because I had to go to the campus, actually not the CHC, but somewhere else, I couldn't really do the live session then. So we're doing it today. Today actually is going to be a very, very, very important introduction to a lot of calculations. You probably have seen some of it already and some flavors of it, but it's really important that we understand every single step. That's why I'd like to have it live, because we're going to go through several processes, mainly four, okay? We're going to go through a process where the temperature is fixed, an isothermal process, a process where the volume is fixed, an isocoric process or an isovolumetric process, it's the same thing, process where the pressure is fixed, called an isobaric process. And we're going to get into the adiabatic process, where there is no heat exchange. I cannot tell you heat is fixed, constant. That is wrong. You cannot say the heat is fixed. Heat is an energy of transfer between two different states, and it's not a state variable. Sometimes the adiabatic process, and in the lab you will see the word isentropic process. That's when the entropy is fixed. The entropy is a state variable, and you can call the adiabatic process also an isentropic process, where the entropy is not changing. So those are the four key processes. So let me get into, before I start, let me tell you something about the plan for today. We have as much time as we need to do this and to do the lab. However, because of the weight of this material that is going to be introduced, and because I've been teaching all morning, I need to take an extended break in between to go get something to eat and sit down. And you too also, because you really need to take some time to basically take the notes, take as much time. And then when we meet later on, hopefully, we just go through the lab and talk about it, and also discover the ins and outs for it. And if need be, we'll leave the session open, and you guys are working in your lab, and you can ask me. I will turn off the camera, I will turn off the video at that point, but you can ask me. I will turn off the recording too at that point, but you can ask me, and I will be basically somewhere in here, and I will come back, and we will go back into the screen basically and fix whatever needs to be fixed. So this is the plan of action. So hopefully you guys are good with it so that we can proceed. Sounds good? Okay. So let me share with you my screen. First of all, let me find it. And where is, let me add a new page in here and call it processes. And let me share. Hopefully you guys have a piece of paper and a pen, because we're going to be drawing and writing a lot. Okay. Let me pick up the chat just in case somebody writes something. Okay. So in the PV diagram, guys, look at where it says processes in here. Yes? On the screen? Okay. Let's make sure I'm sharing my screen. Let me use a black pen. I really don't like the blue yet. Okay, we're going to need colors at some point. So I have a pressure and we have a volume on a PV diagram. So this is the volume and this is the pressure. And this is a PV diagram. So if I take a point on the PV diagram with coordinates of volume given and pressure given. So I'm going to call this one the initial state. So I'm going to call this one volume initial, and this is pressure initial. So this is a point on a Cartesian coordinate system where the volume is the x-axis. You cannot have negative values for the volume. It doesn't mean anything. So this is only the first quadrant that basically can be shown on a PV diagram. So this is your PV diagram. You cannot also have a negative pressure or even a zero pressure or a zero volume. That's why it's only the first quadrant that you can see from a PV diagram. You cannot see anything else but the first quadrant. So it's not a regular Cartesian coordinate system. Okay. I want to go from this initial state. So this is a state that is well defined. In other words, I know what the temperature also. So you ask me what's the temperature. I can tell you the temperature satisfies this relationship. So I can tell you what the temperature is because I'm making an assumption in here that the gas satisfies the ideal gas law. In other words, it has all of the different requirements in terms of density and all of that, so that this relationship holds true. So PV equals to nRT. So if I know the two values of P, then I know what the temperature is. Furthermore, I know what the temperature is, what the energy is. So I'm going to tell you the energy without really giving it an expression because we really don't care for what it is. It is given though, it is fixed, okay? Because whatever, if I tell you it's 10 joules, all I'm going to do is shift the origin from 10 joules to by negative 10 joules and it becomes 0. Because what matters really in the calculations later on is the difference in the internal energy. So what matters is not the actual internal energy, what matters is the difference in internal energy. So we know it's fixed, but if you want a number, it's 12,322. That hopefully you're happy with that number. If not, just add and subtract whatever. But the point being in here is at the end of the calculation, what matters is really the difference in energy, not the exact value. Okay, so we know the internal energy. Those are called state variables because they are known for a given state. That state has fixed values. I want to go from this initial state to, let's say, for example, this state where the volume has changed to a new volume. Obviously, from the picture I drew, the volume has increased. So this is an expansion. So the system went from this volume to this volume, okay, increased in volume. The pressure from the way this point looks like went down. So this is a decompression from the way I drew it. It doesn't have to be this way. Can be whatever you can think of. The pressure can be higher. It could have been compressed and the volume can be less. Okay, so that's something that is possible too. So this is basically my goal is. Excuse me. How do I go from here to there? That is a process. Obviously, there are different ways for me to go. I'm going to take whichever process I can think of is good enough. So I could take this path. So this is obviously a process. That requires some energy. That requires some work, I'm sorry, I should say. Because the energy also and the temperature has changed because the final temperature satisfies this relationship. And the energy, since the temperature is not necessarily the same, must have changed also to a new value. I use the symbol U for the energy. So this is what I mean by the internal energy. Okay. And the internal energy has to do just with the temperature. That's all. Okay. If you go and read through the chapter, and you're required to read the chapter, by the way, you will find that the change in the energy, which really what matters, so U final minus U initial is simply equal to, for this gas, N, which is the number of moles all the way throughout, times the specific heat of the molar specific heat at constant volume, times the change in temperature, T final minus T initial. Okay. Obviously, if the temperature at the end is higher than the initial temperature, the energy of the gas of the system must have went up because this is a positive value. If the final energy, if the final temperature is less than the initial temperature, then in this case, the energy must have gone down because this number is different, is negative. So that is what this number is. So that is what this expression is. Okay. So we have now full description of the process in terms of when to the energy. We have description. If I know, so if I told you 12,321 joules was the initial energy, for example, and if I calculate and this one number turned out to be 100 joules, so I add 100 joules to the 12,321 joules The initial one, that is the final energy. You guys understand? What really matters in this case is not the initial energy and the final energy. What matters is this number for this specific process, okay? What matters is the change in energy from one state to the other state, the initial energy. If the temperature went up, the energy has gone up. The internal energy has gone up. If the internal energy went down, this gas would have went down, okay? Obviously, if you guys remember from the class, for a monoatomic gas, CV was 3/2 of an R. For a diatomic gas, CV was equal to 5/2 of an R. And for another gas, it's going to be, and for solids, 3R. And for another gas, it's going to be whatever number that, usually it's around those numbers, okay? Slightly more than an R, okay? That is basically what the specific heat is. Okay, it has the same units of the gas constant, because this number, remember, R is a fixed number. R is just based on experimentation. It is 8.314 joules per. It's a joules because this is joules per Kelvin and per number of moles. Now, you have to remember that this expression is only true in Kelvin. So if my initial temperature was 20 degrees, I have to convert that to a Kelvin, which is probably a 273 plus 20, that's 293 Kelvin. So this expression works in Kelvin, not, so if I apply the numbers in here, this is in Kelvin. Same thing in here, this is in Kelvin. So you have to remember that, okay? If you do that, you're in good shape, okay? Don't use the calorie. If you use the calorie, that's fine. Then you have to come up with the correct constant for that, okay? Now, this is basically, so this is will be a time and a half. So it's going to be about 12, basically, joules per Kelvin. And this is going to be per Kelvin per mole. And this is going to be, what, 5/2. So you do the math, okay? You do the algebra, about 20 or something like that, okay? So you do the algebra for it, and you will find the answers for this one. It doesn't matter. So this is basically what we have seen so far. The process in here has two components according to the first law. Two ways for me to increase the energy of a gas. Either do work against it. Take a gas. Here it was. Let's say, for example, this is a piston that I can move. Here is my gas, okay? Press against it hard. If I do that, there will be little space for its particles to move around. So in this case, their agitation becomes higher and higher, and the internal energy increases. So that's one way for me to do that. So this is doing work against the gas. That's what I'm doing. I'm moving the piston down on it, okay? Obviously, so in this case, the energy will increase. U will go up. If I fix the piston, let's do it another way, okay? Let's take the gas, the same gas, and put it in an enclosure, and now take the same piston now and fix it. So come with the, tighten it with screws or whatever that is that you have in here, so it doesn't increase. Of course, you cannot compress it now because the piston is not movable. And it cannot move up because then it cannot do work against the environment, okay? So in this case, what I can do actually too is give it heat, heat it up. So I can take in here and put it on a furnace, for example, and have the flames coming in here and add heat to it. That too would result in an increase in the internal energy because the temperature starts to rise. And as the temperature starts to rise, the internal energy of the gas increases. So U can go up also if I add heat. So this is add heat, okay? The reverse of these two processes will result in the opposite. So if instead the gas expands, then it's going to do work against the environment. It must cool down because that energy must come from somewhere. Imagine with me that somehow the piston is moving against the surrounding environment, okay? Where is that energy going to come from? It must come from the internal energy of the gas. So now, if the gas works against the environment, then in this case, clearly U is going to be going down. Okay? If somehow, instead of putting it in contact with a heat source, I bring ice in here. Let's say, for example, this one was hotter than ice, then heat will escape, remember, from my gas to here, and it's going to cool down. In other words, its energy is going to cool down. So now U will go down, the internal energy down, if I extract heat. This is add heat, there is no up or down. Extract heat from it, okay? So that is basically what's going on in here. So what the first law says then is the following. The first law says in here is the change in energy is equal to the amount of heat added plus the work that is done against the gas. That is basically what that is. So in general, you can do both. Add heat and do work against. That's it. Now you all of a sudden have an internal energy that increases, and vice versa. This is your first law. Okay? That is the only way. I mean, you can end up with a scenario where there is no heat added or no, I mean, there is heat added and there is work done by the gas, and at the end they cancel each other. Let's say, for example, imagine with me that I'm heating the gas and allowing it to expand in the same time. So what I'm doing in this case, I'm adding heat in here, and if I'm adding, let's say, for example, I added 5 joules of heat, then if this one expands just enough so that it loses 5 joules, so then in the end, delta U is 0. You guys see that? That if this is positive 5 and this is negative 5, at the end, I'm back to the energy is not changing. Okay? So that is how the first law is stated. Now, the work is force times displacement, if you guys remember. Yes? Force times distance. So imagine with me, I compressed it. Okay? And the compression is delta Y. The piston in here, so I'm taking a real piston now. The piston has a base of area A. So force that I'm applying in here must be just enough, because I'm doing this process in a fashion that I'm going to describe quickly, called the reversible process. So I do it very slow. So this process must be reversible. All of the descriptions that I'm talking about must be extremely slow. Why do I require that it has to be slow? Because I want this relationship to be true all the time, PV equal to nRT. In other words, this relationship holds only when the gas is settled, not when it's transitioning. So even though I described this wiggly path in here, I'm assuming that at any point PV equal to nRT, that means the gas is in actually thermal equilibrium at all times. And for me to do that, I have to be extremely slow to going from step to step to step to step so that I reach my final point. So this is an ideal situation. That means at any given point, I can go back through the process. Okay? So yes, Nalash, do you have a question?
Yeah, I looked up the equation for the first law, and it said delta U equals Q minus W rather than plus W.
That's a good point to mention, because that's a convention I don't like and I'm not going to use. And hopefully you guys will pay attention to the next point, okay? They use a minus in here because they define the work differently with the minus, okay? So hopefully you guys will pay attention to that detail. This is a standard, actually. It's used in this fashion. It's more symmetrical. Actually, if you look at the total energy of a system from physics 250, from first physics, the potential energy was defined with a negative sign so that you can say the total energy is the kinetic energy plus the potential energy. This is in the same fashion. That's why I use the plus in here, and you will see why. I'm glad you mentioned it because I was coming to that point too at some point. Okay. So let's find the work now. So the work is force times distance. And the force that needs to be overcome is the force that is resulting from the pressure. If I want to compress this gas, do you guys clearly see? So if I want to push the gas with a force F, I need to overcome the pressure, and I have to do it in a fashion so that there is no acceleration. I have to do extremely slow, okay? So in this case, the pressure is, of course, force times area. That's what the pressure is. And this is where the force resulting from the pressure is pointing. And this is where the displacement is. So this must be a work that I need to provide. And this work is clearly negative. So I'm going to call this one delta Y, delta W, and this is where the delta Y. Do you see now the sign where it appeared again? It appeared in the definition of the pressure. So if I write it this way, Nilesh, and that's a very good question, then I'm in good shape. I can say delta U is equal to Q minus P. Okay, what is that area times delta Y? That is actually delta V, the change in volume. Because that is the height that changed in volume times the base area. Make sense? Yes, makes sense? Okay, so that is where delta V is coming from. And now we're back into the fashion that the book has written it. So it's still, as far as I'm concerned, Q plus W, except I'm defining W as being equal to minus P delta V. You see the difference, Nilesh, because you asked that question. They have it Q minus W, and they define W as P times delta V without the minus sign. So everything should be the same now.
I kind of see it now.
Okay, so they have in the book, delta U is equal to Q minus W. And they define W in the book as P delta V. It's the same, algebraically, you're going to get the same things for delta U, that is. Yes? Okay, here is why this notation, the one I'm using, is better. Because it helps you answer the questions right away in your problems. Let me tell you why that is. When you compress the gas, does the volume increase or decrease? When you compress the gas, does the volume go up or down when you push it, the piston down? So is the volume going up or down? Okay, since it's going down, and if I multiply it by a negative number, negative times negative, is that positive or negative? Okay, the volume is going down when I compress. Let's look at this scenario. So when I compress, you guys agreed that delta V is negative, yes? So that means W is positive, correct? Because I have a negative in here. Negative times negative, so it's going to be positive, correct? Yes? Since it's positive, that means the energy of the system is going up according to this convention. Because I add something in here. So when I compress the gas, the energy of the system must increase. So this picture is correct. Make sense? Natalie, you're not, I don't have your camera, so I don't know if you're okay with this stuff or not.
I'm good with it.
Okay, very good. Nilesh, are you following? Because you asked the question, so we're not going to move until you tell us you're good.
I'm good. I think I understand it now.
Okay, so let me explain why this convention is easier. Again, one more time, so that we're 100%. If I do W is equal to minus P times delta V, when I compress the gas, think only of the compression, because the decompression is just the opposite. When you compress the gas, when you make its volume less and less, this number obviously is negative. Because the volume was this much, now it's less, it's by this much. since the delta V is negative, and I'm saying multiply that by a negative, so the negative times the negative is going to be positive. So that means, according to the way we wrote it in here, the delta U will go up. Okay. Whereas in here, you're going to find, because delta V is negative, so you're telling I'm adding a negative value of energy. I'm adding a negative 10 joules, and then you're subtracting a negative 10 joules, you're going to end up with a positive. So in either case, if you're careful enough, you're going to get with the correct answer, but this makes more sense to me. When you are compressing the gas, you're adding energy with exactly the value of W to it. When the gas is decompressing, well, let's say, for example, it's going up in volume, then delta V is positive because it's increasing in volume, then in this case, W is negative. So it's an energy lost. So when the gas is going up in volume, so it's an energy lost. We lost, let's say, for example, you calculate and it's 10 joules. We lost 10 joules because the number is negative. Then in this case, where did that energy come from? It must come from the internal energy of the gas. So this is the first law, okay? Okay. Obviously, this process is not a realistic process. I mean, you might end up with some processes that are not standard. We're going to focus on only the following processes. I'm going to take this one. This is a process. It's called at constant temperature. So T is fixed. So for this one to work, I'm going to assume that T initial and T final are the same. So this is called an isothermal. Okay. And we're going to calculate what in the word is Q and what in the word is W. What happened to delta U here? Obviously, delta U is equal to 0 because the final temperature and the initial temperature is the same. So delta U is 0 in an isothermal process. We don't have to worry about that. Another process that we're going to think about is a process to going from here to here. This is at constant volume. At constant volume, W is 0 because the volume is not changing. Delta V is 0, so W is 0. So again, this is an isocoric process. Delta V is equal to 0. That's what it means. V final and V initial are the same. Both of them are VI, by the way, in this picture. So that means W is equal to 0 because remember, W is this value, the pressure times delta V, and delta V is the same no matter where you are on that cycle. But Q is something. We need to find Q. Once we find Q, we find U, delta U, that is, because according to the first law, delta U is Q plus W. Where is the first law? But W, we just found it to be 0 in here. So if W is 0, then delta U must be Q. So if we find Q, we find delta U. Okay. The third process I'm going to talk about is this process going at constant volume. I mean, constant pressure. I'm sorry. Okay. Obviously, from this temperature to this temperature, it has changed. So delta U is not equal to 0. Q is not equal to 0 either. So we need to find it. W is not equal to 0. As a matter of fact, the volume has changed now. And everybody is not equal to everybody. The temperatures are not the same. This T here, not this T. This T here is different from this T. So the temperatures have changed. So everybody has changed. This process is called an isobaric process. Okay. The fourth process that I mentioned before is the isentropic process or the adiabatic process, which we're going to discover. Okay. So let's talk about these three processes first. Since the blue is isothermal process, let's start with this one. So I'm going to draw the PV diagram again. Hopefully you guys have enough room to draw it. This is the initial temperature, the initial volume. This is the final volume. I mean, the initial pressure. And this is the final volume. and this is the final pressure. And I know that this is an isothermal process. The temperature is fixed. This is the isothermal process. In the isothermal process, as I was saying, at any given point, I know P times V is equal to nRT. And this is constant, by the way, because the temperature is constant, R is constant, and the N is the number of moles, which is constant. So everybody's constant. So this is a constant, which is like a 12, okay? Whatever number you can think of. 27.235, okay, if you like, okay? So that's a number. But the pressure is definitely not constant. We went from this pressure down to this pressure, and the volume is not constant. So these two terms independently are not constant. So I can write P as a function of V simply as just being this constant divided by V. And it can go at any given point in here when the volume was some volume to the next volume where the volume has changed by an amount dV and find the work associated with it. So according to this expression, delta dW is equal to minus PdV. And this is dV. And this is the average pressure. So it's actually this area. That's the work. It's that area. If I make dV as small as possible, it's that area, that's all. All I have to do to find W is just integrate from this value to that value, and that's we know how to do. So W will be the integral from the initial volume, because the variable in this case is the volume, which is VI, to VF of dW, which is equal to minus the integral from VI to VF of this expression, P as a function of V times dV. And P as a function of V on this idea, and as this isothermal, it's always a constant divided by V, and that constant is nRT. So in this case, W is equal to minus the integral from V initial to V final of nRT dV over V. This is a constant. That's why it's an isothermal. That's because it's an isothermal. It's just like a number. So we're going to get it out of the integral, and at the end of the day, we will have a simple integral to do. So the work in this case, for this process, and this process only, not always, for this and this process. So the work depends on the process. For this process, for the isothermal process, because it's not a state variable, so that this does not work all the time. Minus nRT, which is constant, the integral from the initial value to the final value of dV over V. Can anybody help me with what the integral of dx over dx is? You guys remember from your calc classes? You're going to see this integral a lot.
Is it just one?
The integral of dx over x. Isn't this the correct answer to it?
Oh yeah, now I remember.
Okay. Okay.
Yeah,
Do we?
rules.
Yeah. Okay. Is that the answer, or should we add the speed of light to it? Yes. Okay. Since it's a bounded integral, it doesn't matter about this constant. So it's going to be minus nRT ln of V evaluated between the initial value and the final value. And this is going to be ln of VF minus ln of VI. And this is actually going to be ln of VF over VI. Do you guys remember this property of the natural log? From your calc classes? Yes, no, maybe? Yes, does this ring a bell from your math classes?
Yeah, I remember. I took calc like over a year ago, calc 2.
Okay. Okay, so let's summarize this thing because it's important. We found a very good result in here that can help us do a lot of our problems. In And again, I cannot emphasize how important this statement is. In an isothermal process, the work is going to be minus nRT, natural log of the final volume over the initial volume. I took it, the volume at the end is bigger than the volume at the initial. I took VF in my example bigger than VI. That means the natural log, in this case, of a ratio that is more than 1, this is a positive number, which means that indeed this number is negative. Because N and R and T are positive numbers, since this is positive, then the work in this case must be negative because of this negative sign. So if the gas really expands, that means the gas does work against the environment. So the energy must come from somewhere. That's what that negative sign is. Okay. In the book, probably you will find with a plus sign. Please have the correct interpretation for it. If the final volume is bigger than the initial volume, the gas must have done work against the environment. The energy must have come from somewhere, from the gas itself, okay? Cannot be coming from the environment around it. So according to this picture, the way we drew it, the gas actually went up. Now, if the gas went from this volume back to this volume, so it went from this VF down to VI, then this ratio would be flipped. And in this case, this ratio of a negative number, of a fraction, will be less than 1, and the log of less than 1 is going to be negative number times the negative is going to be positive. So if indeed the gas is basically compressed somehow, where the volume went down, the natural log will be negative times the negative is going to be positive, and the work actually will be positive. So we must have added the energy to the gas. So the gas must have taken the energy and did something with it, okay? In the form of work. That's how the energy is being added. Let me go back to this process and talk about the energy. I know delta U is equal to 0 in this process. The reason why delta U is equal to 0 in this process is again because the temperature doesn't change. Delta U is equal to 0 since delta U is actually equal to NCV delta T. This is true all the time, always. Since delta T is equal to 0, because this is an isothermal process, that means the temperature doesn't change. Since it's an isothermal process, that means by consequence, delta U is equal to 0. And hence, since delta U, according to the first law, is this number, that means that immediately that Q is equal to minus W. And since I just found W to be a negative nRT times the natural log of the ratio of the volumes, then in this case, Q must be a positive nRT ln of the final volume over the initial volume. That's exactly what that number is. Okay. Look at this expression. According to the picture I drew, the final volume is bigger than the initial volume. So the ratio is positive. Okay. The natural log of a not positive, and the ratio is bigger than 1. So if the ratio is more than 1, the natural log is positive in this case. Since the natural log is positive, Q is positive. So here is what's going on in this process. I'm going to draw it with a different picture, that's with a different color. So heat, which is positive, is taken from this reservoir. This is a heat reservoir now, because its temperature never changes. We're taking heat from it, and we're doing work in this expansion in such a way that Q plus W is equal to 0, because the temperature is not changing. So we're taking heat and doing work. How much work at the end we did? Actually, we did this area. This is the actual work. That is that area that we calculated. That's what the definition of the area is. Does this process make sense to you guys? We calculated everything for it. Work, heat, and energy. Make sense? So far, so good? Okay, we're gonna move to an easier process. Which color did they draw that? The red one, the isocoric process. So this process is somewhat easy, okay? So in this case, delta V is equal to 0. Since delta V is equal to 0, that means dV at any point is equal to 0. That means dW is equal to 0. That means W is equal to 0. Integrate 0 over bounded limit, because this is a bounded integration. You're going to get 0. So it's a constant evaluated between two ends. It's going to be 0 no matter what. In other words, the area going from this volume to this volume, there is no area. That's what the work is. It's always that area. And it's clearly the reason why it's negative in here. It's very careful that you look at the negative number. We found that negative. Let me go back to the isothermal process for a moment, okay? It's negative if the volume at the end is bigger than the volume at the beginning. Let me explain why that turned out to be negative. When I went from this point down to this point, I was describing this area in a fashion that is actually clockwise. And if you remember from your angles from way back in physics 1 and 2, is that when you go in the angles clockwise, it's a negative angle. Yes? And it's counterclockwise when it's positive. At some point, we're going to be doing cycles. And the cycle, you have to pay attention to the sign for it. Which way are you going around it? Are you going clockwise or counterclockwise? If you're going clockwise, the work is going to be negative. And that will turn out to be an engine. So engines, clockwise. Because W is negative. That means it's doing work for you. It's working, doing stuff for you. Whereas if you go counterclockwise, it's a system that is having work done against it. It's actually extracting heat from somewhere else. So it's a heat pump. A heat pump will go counterclockwise. It's in the opposite, basically, where the area will be positive. In other words, you have to do work against it, like the refrigerator. The refrigerator or the AC unit in your house is actually taking energy from the outlet and extracting heat from the house and dumping it outside. Okay, so that's a heat pump where W is going to be positive, but that's counterclockwise. You see now, Nailish, and why that question was extremely important and why I use this convention, because it makes sense and connects to the angles also. When you go counterclockwise or counterclockwise, you'll have W that is positive. Okay, W that is positive. Yeah, W that is positive. So you must be adding energy to the system. Okay. Wait a minute. Yeah, it's. This is about cycles, okay? Not processes. And I mentioned at the beginning about the cycle. But I want to bring your attention to the signs in here. The reason why it came negative in here, this is a process going from point to point. The reason why it came negative is because we're going clockwise. We're going with the clock. Okay? The number turned out to be negative by itself. If we were going in the opposite direction, the number will be positive. Okay, so let's continue with this process in here, the Isocoric process. So now we know in this case that delta U must be equal to Q, and I know this number is NCV delta T. So that's the answer to Q. Both of them are equal because W is 0. And from the first law, delta U is Q plus W, and W, I just argued it's 0 in this process. Okay? So this process is somewhat easier than the first one, because we know what delta U is, we know what Q is, we know what delta W is for this process. Let's look at the third process, and that is the isobaric process. This requires some work. Because remember, in this process, I cannot say that the W is 0 or Q is 0 or anything is 0. So I really have to work with all of them, okay, to find them, delta U, Q, and everybody. So let's start with this one. Let me draw this one because it really requires some pictures in here. So again, this is V, the volume. This is the pressure. The pressure is fixed now. So the pressure is not going to change. The volume can change though, from V initial up to V final. This temperature will satisfy P, which is constant, times V initial must be equal to nRT initial. Because something has to give. If the pressure is fixed, then the temperature cannot be fixed. Temperature must be different. And this is P times V final is equal to nRT final. So the temperature in here is some isothermal, which is not the same isothermal as this one. So we're going through this process now. Okay. We are going to define the molar specific heat at constant pressure so that Q is equal to NCP delta T. Because I can find what the T final is. I can find what the T initial is. If I know what my volumes are, from here I can find what I can find what delta T is. And since that's the case, then I can use this definition for CP, and from here I have the heat. So this is the heat. Similarly to how we found in here, this is the molar specific heat at constant volume, because this is an isobaric process. So we're defining an isocoric process, I'm sorry. This is an isobaric process, so we're defining in a similar fashion the heat that way. Now the energy, of course, delta U is still given by NCV delta T. So it's still true. This is true all the time, we said, including in this case too, okay? Now I need to find what the work is. The work is simple in this case too, actually. The work, W, is equal to the integral from the initial volume to the final volume of PdV. But P is constant in this process, remember? P is constant. So it's because this is an isobaric process. So this will come out of the integral. And this will be simply equal to minus P times the integral of VI, VF of dV. So basically I need to integrate dx. What's the integral of dx? That's probably the easiest integral in the book. What is the integral of dx? I've seen so many things that we start to forget the easy ones. Yeah, I know it's on your tongue.
Is it x squared over 2?
No, that's the integral of x dx. This is just the x.
Oh, I see.
Yeah. So it's basically, if you guys remember, x to the power 0 dx, all I have to do is just add 1 to it, 1 plus 0, so it's x to the power 1. In other words, if I take the derivative, I just find this is a constant. This is 1, okay? So plus the constant. So at the end of the day, basically, the work is going to be minus P, which is fixed, by the way, in this process. This is an isobaric process where the pressure doesn't change at all. So it's the same pressure all the way throughout, from here to here. So in this case, minus P times the final volume minus the initial volume. Obviously, if the final volume is bigger than the initial volume, this number is positive. And the whole number is going to be negative. So indeed, in this case, the work is done by the gas because it went from initial volume to a final volume. However, the energy now also has changed. If this is the picture, then it must gone up. So the gas did work, and yet in this case, its internal energy went up. So something must have gone up too. The heat also must have been enough so that the energy must have gone up. So here is the deal. Delta U went up, which is equal to Q plus W. And this is actually negative number from here. You can clearly see it's a negative number. So this is a negative number. Q also must be bigger than W by just the right amount. So let's look at a different isobaric process, okay? Here is the isobaric process that I want to analyze. I want to go from the volume V up to the volume V plus dV. In other words, this is an infinitesimal displacement, not an exaggerated one. The pressure is always fixed, okay? The pressure is P. The temperature changes from T to T plus delta dt. So I want to look at this process much, much smaller on scale, not the big scale, okay? So in this case, it's going to give me du, because the energy must have gone from U to U plus du. So du must be equal to ncv dt, the change in temperature, and it's equal to the amount of heat plus the amount of work that is done in this infinitesimal spaces. I know this quantity is already equal to ncp dt, and this quantity is equal to minus pdv. This is all true. The only question is to find this expression. Let me go back to PV equal to nRT, because I know that's true all the time. PV equal to nRT, since the only thing that changes in here is the volume, so during this change from the final to the initial, this gives me PdV equal to nR dt. Okay, think of it this way, and later on it became to PV plus dV equals to nR T plus dt, and subtract these two expressions because I know PV equal to nRT, so this cancels from this side, and I will end up with this expression. This is differential form, no more, okay? So, so this gives me that expression, PdV equal to nRT. So I need to sub this value here. This is from the ideal gas law. This is true all the time, okay? And the reason why I'm saying this one is true is because I'm taking this process to be a reversible process so that this works. So I'm going to take this expression PdV and sub it all the way back in here to find that this expression now for the energy, on one side, it's ncv dt. On the other side, it's the sum of the heat plus the work. And the heat, in this case, it's ncp dt. And the work, which is minus pdv, is actually minus nr dt. Because of this expression here using the ideal gas law, because P is fixed. We are through an isobaric process. We are through a process where the pressure doesn't change. So this will turn out to be minus nR dt. Obviously, I took it between two arbitrary points in here, V and V plus dV and T plus T dt. So it doesn't matter this, they should cancel out. So the dt cancels from both sides. The n, I took an arbitrary number of moles n, so they cancel also. And there is a relationship between CV and CP and R, which gives me, which is usually written as CP is equal to CV plus R. This is true all the time. I took it between two infinitesimal processes and an isobaric process, and gave me this relationship between the specific heat at constant, the molar specific heat at constant pressure and the molar specific heat at constant volume. And the difference between them is just a constant, which is 8.13. So this is an identity. And that is the proof for it. So this is very, very important that we guys, we follow this thing. We know where these things are coming from. And from now on, if they give you CV, that's all they need. That's all you need. You can find what CP is. And if they give you CP, that's all you need. As a matter of fact, we're going to define gamma, the gas constant, as simply Cp over Cv. Okay, if they give you gamma, because you can find this expression using this one in here as Cv plus R over Cv, which is 1 plus R over Cv. If they give you gamma, you can find Cv. And if you can't find Cv, you can find Cp. So any of these numbers are good enough for you. So when you're doing homework problems or you're doing exams or something, any one of these things that is given to you, you're in good shape. You don't need something else. You're good. Okay? You're good. So clearly gamma is more than 1. Clearly gamma is bigger than 1 because Cp is clearly more than Cv all the time. Cp is more than Cv all the time. By the difference between them is R. And here it's 1 plus something. And these two are both constants. So it's all more than 1, no matter what. Okay? You cannot have a gamma that is equal to 1 or less than 1. That's going to be a disaster if you have such a gap. Okay, so when you're playing with numbers and trying to do modeling, you have to be careful with these things. Okay, because sometimes you introduce things in your equations that don't make sense physically, because there is no such a thing that is going to exist in that fashion. Okay, so we have gamma. This is by definition. Okay. The only thing that is really at this point of a great interest to us, honestly, is Cv. And after that, we can find Cp, we can find everything, okay, gamma and everything else. So where are we now? We found W for this process, here it is. We found delta U for this process, here it is, because we can find what T final or T initial is. And we can find what Q is. So this process is fully discovered too. But what came from it is this relationship between Cp and Cv, actually, honestly. Okay? That is really important. That is what came off of this process. Okay, we've been together for about an hour. We still have at least another half an hour of full concentration. And then we're going to go on a break, okay? Long extended break. Because it's really heavy stuff. Do you guys sound the weight of it? Do you see the weight of it or not? Okay, so to stay focused, and myself also to stay focused too, so we're going to start with the adiabatic process. So the adiabatic process. I'll try to give it in the big picture and then see what that is, okay? So the last one is the adiabatic process, sometimes called the isentropic process. Okay, so let's see what's going on in here. So again, we're starting from some initial points in here of initial volume VI, of initial pressure PI, and we're going to a final volume VF and final pressure PF in a fashion where there is no heat exchange, where Q is equal to 0. That is what the adiabatic process by definition is. No heat exchange. So in other words, we answered one of the questions right there and there, namely the heat. Q is equal to 0. Okay, that's what the adiabatic process is. Now we need to find W. Once we find W, we know what delta U is. Delta U is simply is equal to W. Okay. Well, we know what W is. W is just the integral of PdV. From the initial volume VI to the final volume VF of this function that I need to find dV. But I don't know what PV is equal to, in this case, what P is equal to. I know PV equal to nRT. But you have to be careful with this expression. The temperature is not the same. The initial temperature, as a matter of fact, can go through an isothermal. This is the first initial temperature. This is Ti, and this is Tf, which is a different temperature. So that I cannot use P equal to nRT over V because T is not constant too. You have to be careful in here. So I cannot sub that expression. I need to find what this P is as a function of V. Once I find it, then I plug into this expression, find W. Once I find what W is, then I can find what the delta U is. As a matter of fact, I can answer this question right there and there, okay? Delta U is equal to NCV delta T, and that is also actually W2. But that is not the big picture. That is actually the correct answer. In an exam, if you know what delta T is, you're in good shape. Of course, if you know what these pressures are and what these volumes are, you can find what these temperatures are. So you can still answer the question if you know what these expressions are. But if you don't, and most of the times you don't know what the final volume is or what the final pressure is, then you have to do some honest work to find what those values are. Because they might give you what the final volume is, but they don't give you what the final pressure is. You need to find it. Or they might tell you the final pressure, and they don't tell you what the final volume is. So you need to find it. It's not like this. If you don't know what the temperature is, you need to find it. So in other words, we have to do some honest work to find what that function P is as a function of V. That is really the challenge in an adiabatic process. We need to find that. Once we find it, we're in business. So let's go back into this expression because this is really the starting point in here, okay? So in an infinitesimal process, du is equal to actually dw, and this is equal to ncv dt, and this is equal to minus p dv, okay? But the pressure now changes, so as a function of volume, and so is the temperature. I know also at any given point that this process is controlled in such a way that PV equal to nRT. This is true. But neither P, nor V, nor T are constant in this process. P changes, V changes, and T changes, okay? So if I want to find the variations in here, I have to be very careful with this expression. This is how I'm going to do it. I'm going to write P. You guys are familiar with the differential forms or not? I want the honest answer in here. If you're not, we can do it explicitly. If not, if yes, we just apply it from your calc classes. Okay, here is the deal. The P was P plus dP. I'm sorry, plus dP. The volume was V, and now it's V plus V dV. Plus, I'm sorry, V dV, plus dV. Temperature is N, it was T, now it's T plus dt. So this is the new expression in new state. We went from a point in space that has coordinates P and V, what's temperature T, where this was true, PV equal to nRT, to a new point in space where the pressure has changed from P to P plus P dP, and volume has changed from V to V plus dV, and the temperature has changed from T to T plus dt, because everybody can change in this case. That's the difficulty with this process. If I expand this form in here, I will have P times V plus P times dV. That's done. Plus dP times V. I'm going to write it V dP. Plus dP times dV. I'm going to ignore that expression, because these are so small quantities that this is of a higher order. This is already as small as is with dP. This is small as is with dV. And this is actually the highest quantity. This is extremely high. And I'm changing with tiny quantities. And if I change with tiny quantities, this will become the product of the two will be tinier. So I'm going to ignore it. Then this too, or that one for that matter. This on the other side is equal to nRT plus nR dt. Obviously, we started from this expression. So this PV cancels nRT because this is true. And I would be left with the following. PdV plus VdP is equal to nR dt. Whereas I know also that NCV dt is equal to minus PdV. I know from this expression what dt is. This gives me dt because I want to find P as a function of volume. So I don't want the temperature in between them at all. So I want to get rid of the temperature. Although the three of them change, I want to get rid of this T because of this relationship. So that's what I'm doing now. I'm getting rid of the temperature, and at the end of the day, I'm going to find what the function P as a function of V is for this diagram. Once we do it, then we can find the final volume, we can find the final temperature, and we can find the work, and we can find the heat, and we are done with this problem. So I'm going to use this expression here because this is true all the time, because there is Q is equal to 0 in this process. Normally, I add Q, but for this process is an adiabatic process where Q is 0. So that's why I'm saying delta du is equal to dw, and du is always NCV dt, and dw is always minus pdv. So this gives me dt equal to minus p dv over n times cv. So this expression, I'm going to sub it into the last expression that I have found, and we should be in business. So this is dt. This is what I'm going to write in here. So this side stays the same. And this side becomes minus, because there is a minus in it, actually. Minus, first of all, I have to keep this nr stuff, n times r, times dt. And dt is the one that brought the minus, pdv divided by ncv. It's pdv over ncv. Cancel the n from both sides. That's good. And move everything to one side. And I already have PDV here, and I have another PDV that came, although with the stuff next to it. So I have, and a negative becomes positive when I move it to the other side. So I'll have a PDV and a PDV. So I'm going to take PDV as a common factor. What I'm left with is a 1 in here, plus, because the negative becomes positive, and it would be left with R over CV, plus VDP is equal to 0. Before I go any further, I know what this number is, 1 plus R over CV. Isn't that just gamma? 1 plus R over CV. We just found it to be gamma. So this is actually gamma for this gas times PDV plus VDP is equal to 0. In other words, I have a relationship between dP and dV. So all I have to do is integrate to find what this function I'm looking for is. So for that, I need to divide both sides or multiply them by 1 over P times V. If I do that, I will have gamma times PdV over PV plus VDP over PV, obviously equal to 0. 0 over something is 0. The V cancels the V, and the P cancels the P. And I will be left with the following expression. Gamma dV over V plus dP over P is equal to 0. This function does not have V in it, so I can safely integrate it. This function does not have P in it, so I can safely integrate it over V. And the integral of 0, of course, is a constant, that's all. So it's going to be on one side constant, and I'm left with the integral of dx over x again, which we just saw earlier. What is again the integral of dx over x?
It's ln x.
Natural log. Yeah, the natural log. Very good. So I have gamma natural log of V now, plus the natural log of P, and that's it, equals to a constant, because the integral of 0 is constant. Okay. And ln of V, actually I can write it ln of V to the power gamma plus ln of p. This is the properties of the natural log, that's all. Okay, remember gamma is more than 1. Okay, now a log of something plus something, a log of something else is just a log of the product of the two quantities is equal to a constant. All I have to do is take the exponential of the natural log, and that is going to be the exponential of a natural log is just p to the power v to the power gamma, and the exponential of a constant is another constant. This is not the same constant, it's another constant, okay? And now look what happened. We found the expression that we needed. So p as a function of v is simply some constant divided by v to the power gamma. That's what we needed to do. Now we know everything about this problem. We know where we started from. Since you give me the final volume, I can tell you what the final pressure is using this expression. If I find what the final volume is, I can find what the final pressure is. If I find what the final pressure is, using PV equal to nRT, since I know what the final volume is, I can find using this expression what the final pressure is, then I can find what the final temperature is. Then I'm going to go back to this expression and find the delta U and also the W for this problem. Remember, Q is 0 for this process. So that is the whole thing to it. Now, you're worried about this constant that appeared in here, no big deal. That constant is the same throughout the entire process, from here to here. Since we know the initial point, that is true also for this process. So that constant must be satisfied initially. So in other words, V initial to the power gamma must be equal to P initial. So in other words, the constant is no more than the initial value of the pressure times the initial volume of the to the power gamma. So in other words, this expression is written this way all the time. P as a function of V, if you like, is equal to the initial pressure times V to the power initial to the power gamma divided by V to the power gamma. We have found this expression. Remember, gamma is more than 1. So we're safe in here, okay? So in other words, this is what we have found. PV to the power gamma is constant, which is the initial value to the power gamma, or if you like, you can write it as the final value to the power gamma. I'm sure you have not seen, were you familiar with this process before in chemistry, or have you seen it at all in chemistry? If you did chemistry. No? Yes, maybe. Or if this is the first time, this is the first time, no big deal. Come on, guys, yes or no thing.
I've seen PV nRT, but I haven't seen like all of this other stuff.
Yeah, I know, it sounds like brand new stuff for most of you. So it will take a little bit of time for it to sink.
I haven't taken Chem 150, 151.
Okay, so it will take some time to sink. So what I'm suggesting we should do, right now it's 12:30, okay? I'm going to go actually outside and get something to eat. Hopefully you guys also will take an extended break right now. We're meeting around 2 p.m. here, okay? Where we go through the lab. The lab is actually an application of these things, because let me tell you how the lab is so that we are in the same page. I really don't want to put more stuff. It's really heavy stuff as is, but I'm going to tell you what that is. Because of PV equal to nRT, I can write this expression now as a PT relationship, not a PV relationship. In other words, in a PT diagram, there is another expression for the adiabatic process. All you have to do is just use the expression PV equal to nRT, get rid of V, and sub it back into this expression, and you will find the new value now in terms of PT in the TP diagram. Or, especially this process is important for the entropy, okay? Or a VT diagram. In other words, get rid of the P in this expression using this relationship, and you will have a TV diagram. Okay, so in the TV diagram, it's a different expression. That's part of the lab that we're going to do later on. And we're going to go through the process and do some oscillations and find this stuff in here. Because of the heavy stuff that we have seen today, and it's a lot, okay, I must admit it's a lot, especially if you have not seen it in the past. We're going to pause extensively. I will send you a reminder around probably 1:55 again to come back to the link, and we meet again for the lab, okay? We'll have a lighter thing. In other words, we'll have dessert later on in terms of the lab, okay? So this is the heavy meal. We're going to have something to eat actually physically, and then we come back for this one. Does this sound like it's a good plan, or are you ready to continue right away? Because I am not. Okay.
That sounds fine with me.
Okay. How about you, Nailish?
I was muted. I said sounds good.
Okay, very good. How about you, Natalie?
Sounds good.
I'm sure the rest of the class, who are only a handful who are not here, they don't mind because they're going to watch this stuff recorded anyway. Okay, so I'm going to stop sharing these things. Enjoy your meal. And I will see you guys around 2 o'clock, hopefully, after we have this thing processed. Okay? Thank you, guys. And if you have any questions while you're thinking about it, please do, okay? Especially this thing. It might look strange, so it's a good idea while you're eating, think about it, and hopefully bring some questions later on. Thank you. Thank you, guys.